So in this question, there are two parts that we are required to solve. The first part is that we need to find out the Hamiltonian or H for two non-interacting identical particles, right? And they are in an infinite square well. The second part of this part is that we need to verify that the Fermion ground state is an eigenfunction of the Hamiltonian with the appropriate eigenvalues, right? In example 5.1, right? So let's start with its solution. Its solution is very simple, right? So we need to prove that the function, a wave function of x1 and x2, it is an eigenfunction, right? Let's say that I'm writing eigenfunction is EF, right? Um, of a Hamiltonian for two non-interacting particles in an infinite square well, right? So this function's equation would be something like this: x1 x2 is equal to under root 2 divided by a sine pi x sub 1 divided by a sine 2 pi x sub 2 divided by a, and negative, since I am running out of space over here, so I'm going to write it in the next line, right? So over here I have sine 2 pi x1 divided by a and sine pi x sub 2 divided by a, right? So now we need to find out this Hamiltonian, right? So this equation would become Hamiltonian, right? Wave function of x1, x2, right? That is equal to e times the wave function of x1, x2, right? So the next step is that we need to plug in the value for e, right? So let's plug it in, and that is h cross square divided by 2m, right? That is an equation that we already know. You just need to recall your previous knowledge. Del 1 square plus del 2 square, right, times the wave function of x1 and x2, right? So from here what we are going to do is that we need to partially derive this wave function, right? So we need to partially derive it with respect to x1 and then with respect to x2. So let's write down the equations for that, right? So the and we need to partially derive it twice, right? So we have delta square wave function divided by del x1 square, so that is equal to under root 2 divided by a square bracket negative pi square divided by a square times sine pi x sub 1 divided by a sine 2 pi x sub 2 divided by a plus 4 pi square divided by a square times sine 2 pi x sub 1 divided by a, and it is multiplied with sine pi x sub 2 divided by a, right? Square bracket closes. Now this is the equation for the partial derivative of uh, twice the partial derivative of the wave function with respect to x1. Next I'm going to write down the equation for partial derivative of wave function with respect to x sub 2 square, right? So that would be under root 2 divided by a negative 4 pi square divided by a square into sine pi x1 divided by a times sine 2 pi x sub 2 divided by a plus 1 times pi square divided by a square sine 2 pi x sub 1 divided by A into sine pi x sub 2 divided by A square bracket closes, right? So now what we are going to do over here is that we are going to plug in these values of partial derivative of the wave function, right, over here in this equation, right, this del 1 and del 2 square. So let's plug it in and we'll get an equation that would be Hamiltonian of the of the wave function x1 and x2, that is equal to a squared divided negative a squared divided by 2m negative 5 times pi square divided by a square, parenthesis close, under root 2 divided by a sine pi x sub 1 divided by a sine 2 pi. um Let me erase it and write it in the next line because there is not much space over here. So that is multiplied with sine 2 pi x 2 divided by a negative sine 2 pi x sub 1 divided by a into sine pi x sub 2 divided by a, right? So the next step is to simplify it, right? So when we'll simplify it, we'll get a very simplified form of this equation. So that would be uh, Hamiltonian of the wave function x1 x2, that is equal to 5 times a square h cross square times pi square divided by 2ma into the wave function x1 sub x sub 1 and x sub 2, right? So now this over here is basically um, e, right? So this is e is equal to 5 h square times pi square divided by 2ma square, that is basically equal to 5k, right? So next what we need to do is that the second part is that we need to find out the next two excited states beyond the one example 5.1. Wave functions and energies for each of these three cases, distinguishable, identical bosons, and identical fermions, right? So let's start with that. Now, the first part is that for the distinguishable distinguishable particles. Okay, so for distinguishable particles, we write the total wave function as a product of wave function sub n1 n2 x1 x2, that is equal to 2 divided by a sine n sub 1 pi x sub 1 divided by a times sine n sub 2 pi x sub 2 divided by a, right? So now we have that e is equal to n sub 1 square plus n sub 2 square times k, right? The excited second excited states would be n1 is equal to n2 is equal to 2, right? So we're going to plug these values right over here, so that we have wave function 2 2, right, of x1 x2, that is equal to 2 divided by a sine 2 pi x sub 1 divided by a times sine 2 pi x sub 2 divided by a, right? So from here we would get that energy sub 2 2 is equal to 8k, right? So and that is non-degenerate, right? And that is non-degenerate. Fine. So the third excited state, right? The third excited state, it would be degenerating, right? So degenerate, and for that we would have n1 is equal to 1, n2 is equal to 3, or you can say that either n1 is equal to 3 or n2 is equal to 1, right? So we would find out the equations for wave function respective first for this case and afterwards for this case respectively, right? So we would get that the wave function 1 3 would be equal to 2 divided by a sine pi x1 divided by a sine 3 pi x2 divided by a, right? And the equation for wave function sub 3 1 would be 2 divided by a sine 3 pi x1 divided by a sine pi x2 divided by 8, right? And from these two equations we would get that energy E sub 1 3 is equal to energy 3 1, that is equal to 10k, right? Now this was the solution for first part of the B part, right? Next we needed to find out for the identical bosons, right? So next part is the identical bosons, right? So for an identical boson, the total wave function is written in this equation: wave function psi sub n1 comma n2 of x1 comma x2, that is equal to under root 2 divided by a square bracket sine n1 by x1 divided by a sine n sub 2 by x sub 2 divided by a, plus I'm going to write the next time in the next term in the next line, right? So that is sine n2 by times x sub 1 divided by a sine n sub 1 by x sub 2 divided by a, right? So next what we are going to do is that we are going to write the excited state, right? So just as we did for the previous case in which the excited states were n1 is equal to n2 is equal to 2, right? So we'll just plug them in over here, right, in this equation, so that we get a wave function 2 to x sub 1 x sub 2 is equal to 2 divided by a sine 2 pi times x sub 1 divided by a into sine 2 pi times x sub 2 divided by a, and you would get that the energy over here is equal to 8k, right? That is similar to the energy that we found for this case when we had distinguishable particles, right? So next, similarly, we're going to use the same values for the states um, when n1 is equal to 1 and n2 is equal to 3, right? So that would be over here, that would be non-degenerate, right? So we just plug them in the wave function equation, right? So that is wave function 1 comma 3 x1 comma x2, that is equal to under root 2 divided by a square bracket sine pi x1 divided by a sine 3 pi x sub 2 divided by a plus sine 3 pi x sub 1 divided by a, and that is multiplied with sine pi x sub 2 divided by a. Square bracket closes, and right from this equation we would get that energy sub 1 3 is equal to 10k, right? So this was the solution for the identical bosons, right? And the last part is that we need to find out the solution for the identical identical fermions, right? So similarly, first of all, you would write the wave total wave function, right? So that would be um, psi sub n1 comma n2 of x1 comma x2, that is equal to under root 2 divided by a square bracket sine pi times x1 divided by a sine 3 pi times x sub 2 divided by a negative. Again, I'm running out of space over here, so that would be sine 3 pi times x1 divided by a and sine pi times x2 divided by a, right? And from here we would get that the energy is sorry, I made a mistake over here. I just plugged in the values, right? So these are the values for n1 is equal to n2 is equal to 2, right? So no now the values of n1 is equal to n2 is equal to 2, they does not exist in the case of identical fermions, right? So these are the values. This equation is for the values um, when n1 is equal to 1 and n2 is equal to 3, and that is non-generate, right? So from here we would get that the energy is equal to 10k, right? The next values that we would plug in over here in this equation, that would be n1 is equal to 2 and n2 is equal to 3, right? Similarly, you will plug them in and you will get that the energy for 2 3 would be equal to 13k, right? um this is very simple. I have not substituted the values over here for the identical fermions because they're very simple. They're just similar to the above parts that we did, and you can do them by yourself. um but I have written the solution, the final solution, right? And I have also explained it. So I really hope that you will be able to do it on your own. Thank you very much for watching the video.